All right, everyone. I am here with Yanshuai Cao. Yanshuai is a senior research team lead at Borealis AI. Yanshuai, welcome to the TWiML AI podcast.
Thank you for having me, Sam.
Awesome. I am really looking forward to digging into our conversation. We'll be talking about Turing, which is a recent project that you've been working on that does text to SQL. But to get us started, I'd love to have you share a little bit about your background and how you came to work in machine learning.
All right. So I did my undergrad at the University of Toronto in computer science and math and stats, and I took a number of AI courses during undergrad, and that gave me the opportunity to work in the computer vision lab run by David Fleet at U of T, and so I did two summer research projects there, and afterward went on to do my PhD with David, co-supervised by Aaron Hertzman. And I did my PhD in actually in Gaussian processes, not in computer vision. And Gaussian processes is this class of Bayesian non-parametric models that learn very quickly from small number of data points, and my work was focusing on scaling the compute aspect of GP. And on site, I also worked a little bit on adversarial robustness of models. So this was the time when um, people just found out that you can actually apply this imperceivable perturbation to images and then change the class labels. So
Mhm.
we thought that, can you change more than just class label? Can you actually change the features to make the features like, another image completely, not just change the label? And surprisingly, it turns out actually um, you can actually take a picture of me and then apply a perturbation, change the feature of me to look like feature of a car, for example, not just any car, but a particular car of particular color in that pose, etc. And so that was very surprising at the time. But we thought that this adversarial robustness issue is going to be solved very quickly. But turns out cannot be more further from truth. Things still unsolved problem.
Do you still
Um,
follow that space?
Not super closely, but it still motivates a lot of things that I do. Uh, Especially later, after I joined Borealis, um, I look at that literature and people found out that not only you can do this on vision, you can do this on NLP as well. And obviously, there the perturbation is not imperceptible, change to pixels, but you add some extra text. And also, you can do this in the physical world, apply some patches to images that are not, changing pixels, but some patterns that people don't pay attention to. And they're actually very hard to get rid of. Um, so what that tells is these old, theoretical approach of studying and understanding this adversarial attacks were not actually capturing what really under the hood. Like these people were considering adversarial attacks with like some sort of perturbation within a ball centered at the image and look at the robustness model that way. But
Hmm.
that clearly doesn't capture all the other ones. And fundamentally, what looks like is what the model, how the model represent the data, represent the world, is different from human, from people's representation, and
Yeah.
they're not aligned. And it looks like their models are picking up on sort of shortcuts or spurious correlations or other type of associations that we don't use, and fundamentally looks like that's the problem. And and it looks like you know one has to really um, go beyond pattern matching to really um, to be able to get to the root of this problem. So to look at model that can reason, that can try to discover the type of relationship that people use in recognizing, understanding, and reasoning. So that was my thought at the time, and I think it was also thinking shared by lots of people in the field, and so that led me to work on NLP because NLP is a lot closer to reasoning. I felt because language is already a model of the word, and yeah, also because Borealis is part of Royal Bank of Canada. There's a lot of potential application of text of NLP
Mhm.
inside a bank.
Tell us a little bit about Turing and the motivation for it. How did the project get started?
Right. So Turing is this natural language database interface. It's a demo of a natural language database interface that we built, um, and it's really just putting a lot of our work on semantic parsing this space together in this academic demo. So natural language database interface, the from application perspective, the potential use is to allow non-technical users to interact with structured data set because there's a lot of insight in there, and we want to give the opportunity for non-technical users to get those insights. And from a research perspective, it's a very challenging natural language processing problem because the underlying problem is you have to parse a question asked in English or any other natural language and convert to SQL. And we all know natural language is ambiguous. Machine language is unambiguous. So you have to resolve all the ambiguity in order to parse correctly. Furthermore, what's different from something like convert to Python or other programming language is the mapping from questions to SQL is underspecified if you don't know the schema. It really depends on what is the structure of schema, and so model has to really learn how to reason using it, and in order to resolve all the ambiguity and correctly predict the SQL. And lastly, this you train the model on some domain. You don't want to just work on this domain. You want to work on domains and databases that you never seen before. So that's the cross domain, cross database part of it, and that is very very challenging because it's a completely different distribution once you move to a different domain.
So we're talking about Turing, shortly after the release of OpenAI's Codex, and so I imagine as you're talking to people about it now, that's a correlation that folks make because that project is also focused on code generation. I'm curious, if you might compare and contrast the different projects and maybe the complexity of the challenge or different aspects that would help us understand how they might be similar or not.
Right. So first of all, Codex, I saw the demos, and the demos are really amazing, impressive. Um, I think if you look at the where it's applied, it's focusing on programming language like Python, JavaScript, and all this language where you can find a lot of publicly available training data, like on GitHub and other sources. I think they're trained on code from GitHub. Um, and so the availability of data is a one major difference. When you try to do SQL, as I said earlier, you really have to know the schema, right? There's not a lot of training data for SQL public available. Like people don't post their schema online generally,
Hmm.
so the amount of data is very very small that can be used for even for like multilingual SQL, you can't find a ton of it for training purpose. And so that is I would say like one major difference. So that's also why Turing is an academic demo that we built, whereas Codex obviously with the a lot more data, the model is fairly good, and you can build a product out of it.
Okay. um, you mentioned earlier that one of the elements of this project is kind of reasoning and reasoning on text, and that's a fundamental aspect that allows you to transform natural language to SQL. Can you talk a little bit more about the role of reasoning in this problem?
Right. So one of the aspect is what I mentioned earlier, like it's underspecified, and
Hmm.
it's underspecified due to you have to really leverage schema, and the other part is you have to really have common sense a lot of times. For example, if I say which cities have the most number of employees under 30, um, under 30, that refers to age of employee. Assume that I have a table with age column. It's never mentioned explicitly, but the model has to learn to that under 30 refers to age and have to make that association. So that's common sense. And learning, reasoning using schema. An example is if there's textual evidence for two of the tables, but these two tables are unrelated to each other, and there's no foreign key links, and the model really has to look at how the schemas link together, and the relationship of elements in order to infer that, hey, maybe there's a third table that I need to bring in order to produce the correct sequel. So all of this is an example where something is missing, is causing it to be ambiguous, and the reasoning filling in this missing information allow the model to deconfound the relationship. Otherwise, if the information is not there, and the model can just pick up on spurious correlations shortcuts that makes learning possible during training, which of course doesn't generalize, especially on a task like this where you try to generalize to a new domain, a new schema, and with very small amount of data.
Hmm. And how is reasoning implemented in the model? Is it something that's primarily done at training time, and at inference time it's uh, a single step inference, or is it more something that's done at inference time where you're going through multiple steps to try to reason about a particular query?
Right. So there's few elements in the model that can that express some structural prior about the problem that performs some form of reasoning. One is on the it's a overall it's an encoder decoder type of architecture. On the decoder side, the decoder actually knows the grammar of SQL, and it's baked into the decoder knows has some sort of knowledge that we designed into the model, and it leverages the grammar of SQL to figure out at this step what are the legal things that can be produced, and that allows us to prune search space during inference and during training, and it learns what are the things that are likely. And on the encoder side, it's the model is basically a transformer, but a special type of transformer called relational aware transformers, and can consider the different relations of schema elements, and as well as association between the the question tokens with the elements in the schema, like a table name, column name, and you can give something prior knowledge about this foreign key relationship, and some initial evidence about which token in the question is likely to be linked to which column, uh, and then during training, the model learns to basically clean up this sort of relationship, and during inference, it can basically starting from an initial guess and then try to refine the potential link, and then uh, remove some of the ambiguities.
Hmm.
It's still some. I would say it's still rough form of reasoning. It's obviously it doesn't capture all the different type of things that we wanted to potentially do, but it already make a big difference.
Okay. You talked about how you're part of what makes the model work is that you're providing information to the transformer during training. Can you talk about how the data is prepared and generated to train the model?
Right. So um, during training, basically the model consider both questions and the schema, and the model is actually consists of a pre-trained deep transformer like a Roberta, and on top of it, it has some extra fresh layer of relational aware transformer layers,
Hmm.
and the relational aware transformer layers encode some prior knowledge between elements of you know columns relations and words and words in the questions and words in the column in the table. For example, if for instance if we see a column in the questions, um, if we see a mention of a column of the name in the questions, it provides some initial evidence, and so it has a link there. And during training, basically the model try to maximize the correct prediction. And during that process, it learn to adjust the weight and remove some of the noisy initial links. So
So the relational layers aren't trained; those are, you know, built as priors and then added to the transformer.
they are trained. So everything is
Oh, they
trained
are.
in
Okay.
it. And the relational layers, they are able to take. So maybe let me take a step back.
But are
So
they trained separately from the
now
rest of the
together,
transformer? Okay.
everything is trained together end to end. So maybe let me take a step back. So transformers generally like they can encode, basically they encode the fully connected graph, right? It looks
Hmm.
at, if you ignore the position embedding, it looks like it considers the full sentence as a fully connected graph because every word is associated with every word. And if you take a schema and say that you flatten the schema into like just a long string, like a question, and put it together with the question, and it looks consider everything as a fully connected graph.
Hmm.
What relational aware transformer does is it adds some additional prior information saying that beside this fully connected knowledge about everything could potentially be related to everything else. Um, we have this knowledge of special links like foreign key relations, and if we see mention of car in the question and there's a column called a car type, it's more likely that these two are related. So it bakes this adds this additional inductive bias into the model, and later on during training, it can refine what the initial given evidence into the try to infer what is truly there.
Okay. I think that I think that's consistent with what I thought, but I'm still not clear on where does the initial inductive bias come from? Is that
Right.
trained, separately, or is that, baked in as kind of an engineering process?
So the foreign key relations that's known from the schema,
Hmm.
and the initial link that's given by some heuristics. So that there's some a little bit of engineering there.
Okay.
But even if the schema linking miss some of the initial relations, it's able to
Go pick those up in training.
yeah.
Okay. Okay. Um, Interesting. And so then the entire model is kind of trained end to end, starting with those biases. And training data, the training data set consists of a set of questions that are appended, concatenated with schema information.
Yes, in a way, there's more information. Like there's information about the type of columns that can be used in there. But conceptually, you can think of this as just a graph that the model looks at.
So
So
there's
overall, it's
essentially question natural language queries plus um, some features related to the database, essentially.
Yeah,
Is
yeah,
that right?
yeah.
And the um, there's a kind of a label that is the query that you want returned.
Yeah.
Is it the query that you want to execute, or the results of the query against the database?
It's the query that you want to execute.
Okay.
Yeah.
Okay.
And um, there's this system we trained it on this public benchmark data set called Spider. It's a very small data set, for from deep learning standpoint. But because collecting data for this generally is pretty hard, Spider is the de facto benchmark data set for this problem.
Hmm.
It has 200 different databases, but
Okay.
overall just a little bit over 5,000 queries. So
Oh wow.
it's a very small data problem. Yet you have to learn to generalize to completely new unseen domains.
Hmm. And would it be practical, would you think, to train not on the query that you want, but on the resulting data so that, you can get the same data with many different queries in the database. Some will be more optimal than others. Um, you might want to let the network figure that out.
Yeah, so there are other works in this space that actually looks at user execution result.
Okay.
It's possible, though you have to either change how your model works. So your model still has to produce this discrete objects that executes, and so you either have to change that to some sort of differentiable structure,
Mhm.
or you have to use reinforcement learning or other related techniques to be able to do credit assignments through that.
Okay.
So yeah, so it's possible other people have explored on this problem. It doesn't work super well um, generally. But we have explored combining with our techniques and the denotation, the execution result, to help perform data augmentation afterward, and that improves performance. So in a way, yes, we have additional steps that can leverage the execution results.
Okay. You mentioned a couple of things. One, that the data set is, fundamentally a small data set. You just mentioned data augmentation is one possible way to address that. Are there other things that you have done in this project to kind of optimize the transformer model around the small data set problem?
Yeah, actually one of the key difference that in our approach. So a lot of things I mentioned previously was techniques that were already invented in the field. So
Hmm.
relational aware transformer, we didn't invent that, but where we found out is if you put a very deep relational transformer, you can't train it very well. The models, uh, even if it has ability to perform some sort of form of reasoning, if you can't train it, then it's no use. So we found a way to train deep transformers in a very on small data set in a stable fashion. And so this is very counter to what people used to believe. Like you have, you to train deep transformers, you have to have large data set.
Yeah.
With this technique that we came out with, published at ACL this year, it's possible to train it in a stable fashion on small data set.
And so, what are the key elements of doing that?
Right. So it's in a nutshell, it's a better way to initialize these models,
Okay.
and it also builds on prior works that looks at initializing deep transformer models, and w- where we make a big difference here is uh, we make it possible to actually add these layers on top of pre-trained and then train everything together. So previous techniques that uh, improve stability of this transformer, they were only considering training from scratch. But
Okay.
when you train on small data set, you want to leverage pre-train. You don't want to train transformer, a fresh transformer from scratch completely.
Hmm.
But the previous techniques just doesn't work when you have put the new layers on top of a pre-trained BERT or Roberta. And in a nutshell, well, the how this works is it turns out the problem with transformer training generally is the layer norm layer, and previous work have found out that if you can remove that somehow and still make training stable, the performance is much better. And training transformer generally require you to like have layer norm, large batch size, and learning rate warm up. It turns out you want to remove layer norm, don't do warm up, and here on small data set you have to use small batch size. So we make all these three possible.
Hmm. And when you said you make all those three possible, how do you do that?
Right. So the basically in a nutshell, the idea is you want to there are certain parameters that are in the transformer, either vanilla transformer or relational aware transformers. You want to during initialization you want to scale them by a factor that's proportional to the depth. And
Hmm.
in the paper, we have some derivation show exactly what that scale factor is. And turns out when you do this on top of a pre-trained model, that scale factor needs to be data dependent. And so our method is called the DT fix up, data dependent transformer fixed update initialization.
Okay.
And so when you do that, the model is initialized to basically in a stable regime for optimization with Atom, and it doesn't oscillate, which is the typical problem with that learning rate warm up and layer norm try to fix, fails at doing.
Hmm.
So when you do all of this together, uh, training is stable since the beginning, and you can train your deep transformer. We can, the maximum we trained was 48 layers on this small data set
Hmm.
with very small batch size. The overall data set is just, you know, 5,000, less than, for training is less than
Yeah.
5,000 queries. So you can't use very large batch size.
So instead of the learning rate warm up and the layer norm and the large batch size, you kind of substitute that with data aware initialization that sounds like it does a pass on the data and then scales the parameters and sets your initial weights, and then you get a stable result from the your
Yeah.
training.
Yeah. And what's amazing is once you are able to train this in a stable fashion, the transformer plus relational aware transformer can already perform a lot of the reasoning. The
Hmm.
improvement on these hard cases is huge. So it turns out so what's the learning here is it's already this model can already do some form of reasoning like this. It's just we're not able to train them on this in a stable fashion.
Hmm.
And
And with the initialization approach and its data dependencies, did you find that it was broadly applicable to a variety of data sets, or is it very specific to the benchmark data sets that you used, or other
mhm.
characteristics of the data set?
Right. So we also tried this on a completely different problem, but that also requires reasoning. So a problem for logical reading comprehension.
Hmm.
So so we actually did this after we made all this work in on the semantic parsing problem, and we took that data set, and it's also very small and very hard problem, and we just applied the technique and got very good results. Like without any special engineering on that task, we got
Okay.
near state of art on that problem as well. So generally, yeah, it looks like it's uh, obviously, if your data set is already huge, then you can use large batch size, and
Hmm.
that makes training much more stable. But when you have small data set, you can't do that.
Hmm. And were the data sets, the benchmark data set that you use, was that was that a multilingual data set, or is it monolingual? And what kind of support for multilingual do you have?
These problems are just English, like the reading comprehension and semantic parsing. Uh, but yeah, that there yeah we for semantic parsing there is another data set, but there's no cross language. At least in the popular ones for cross database semantic parsing, there's not simultaneously cross database and cross language.
Hmm. Is multilingual something that you're looking at or interested in?
Yeah, I think it's a very challenging problem. At the moment, we're not studying this problem because there are other like unresolved challenges in
Let's talk a little bit about those. What are the kind of the big challenges or next steps with this work?
right. So generally, data. If you want to continue to improve the accuracy, data is a problem. How to perform data augmentation in this space? I think that's a fundamental blocker, and we are looking at how to do that. In fact,
And it
we
sounds like
have
you did a bit of data augmentation already, right?
yes, actually, we so for the non academic research part of this project, we actually done a lot of data augmentation to
Okay.
make something like this work. But it's challenging. So other people who have done this, their technique is to basically engineer some sort of grammar that can simultaneously produce SQL query and
Natural language.
natural language.
Hmm.
Um, but it's very very tedious, hard task to do, and we actually also tried it, and that was also our first intuition when it comes to do data augmentation in this. But to actually engineer this grammar to produce questions that are very natural,
Hmm.
it's very very tough. So how to do data augmentation without going through hand engineer a generative model for this basically. It's yeah, it's something that we're looking into, and we have some work in progress. It's not yet released, but that allows us to leverage uh, you know knowledge from pre-trained model to actually improve the effectiveness of data augmentation.
Hmm. Um, and before we go to the next challenge, the data augmentation conversation kind of sparked a question around the complexity of the questions and the queries. Uh, can you kind of speak to that and characterize the level of complexity that that Turing's able to deal with?
Yeah, so in terms of query that it can produce queries that involve joins, multiple joins, subqueries. Um, so sometimes you have questions that are in English very benign, very simple. Like this is not an example that are actually on Spider, but say like what's the average return of all the stocks that performed above market average?
Hmm.
So there's compositionality there, and market average refer to like actually depending on the structure of your schema will require you to first compute that number by doing some sort of aggregation and plug it into the top level query, and Turing is able to do things like this, and also obviously it's also able to handle some of the other extreme, like if you write questions in very verbosely, with lots of different conditions, and it can handle a lot of that as well. Now obviously it will have mistakes. It definitely is not yet a system that is quite a level of accuracy that's usable directly as if you want to just trust the result, execution result 100%, it's not quite there yet.
Hmm.
And that's also why, like, for the Turing demo, we built in some system in presenting the end result to help user really make sense of the result and try to judge for themselves whether it's what they want. So what we do is Turing is able to produce multiple hypotheses during its generation, and we explain the hypotheses back to the user in natural language, um, and we highlight the difference across the different hypotheses, and then they can see for themselves. Okay, the difference between these three is, instead of this column, we mentioned that column, and here instead of this value, it's using some other value, or maybe the overall just structure logic is completely different,
Hmm.
and then they can see for themselves which one correspond to their intention originally and can choose that.
Now that explainability model sounds like its own research project. Is that something you worked on internally, or is that kind of an off the shelf technique that you're able to
It's
apply?
our own work.
Okay.
So that part is so we had a number of different publications at ACL this year.
Hmm.
So the work on optimizing deeper transformers, that's one paper, and the Turing demo paper actually consists of the core semantic parser, the component that tries to fill in the value after you get to the SQL sketch, and as well as the explanation module. And the explanation module here, it's kind of different from normal natural language generation, where for at least for research, there's a lot of neural language generation.
Hmm.
Here, we actually don't explicitly don't want neural language generation, because we want the difference across the hypotheses to be only due to the hypotheses themselves, not the natural language generation part.
Hmm.
So we have a very computer linguistics type of grammar based model that can take the SQL and compositionally produce the natural language explanation step by step. And the only difference there is due to the difference in the SQL.
Hmm. And just to make sure I understand that, so you're um, the explainer is explaining the result, not the process for obtaining the result. Is
Correct.
that an interesting nuance? I'm it doesn't sound quite like not wanting to do generation, but it sounds like I'm wondering if there's something missing in not trying to explain the process that won't capture for the end user what the model may have done to get to the result. But I
Mhm.
don't does it even matter?
Well, we think it doesn't. We think because
Okay.
at the end, um, normally, users just care about the final answer, right? So
Hmm.
you can think of SQL as just um, some sort of intermediate representation. Uh, but this is an intermediate representation that actually, could potentially be aligned with how humans think about the problem. This goes
Yeah.
back to what I mentioned, at the beginning, like, the machine's representation of the data of the domain of the
Hmm.
word. How can we make that align with people's representation? So there's lots of intricacy about how the neural net maps the questions and reason and maps
Right.
to the final. But that details might not be interesting to end user. Sort of like when you and we speak, I don't know everything that goes on inside the
Sure.
neurons of your brain, like you don't know, but we have a shared language, and that discrete
Yeah.
representation allows us to have a shared understanding.
Yeah. Maybe another way to put it, the problem that you're trying to solve is that the machine is going to spit out SQL that the user didn't write, and so the user may have some difficulty understanding what's actually happening. If you can explain to the user what this SQL is doing, they
Mhm.
can more easily determine if it's what they expected or what they need. And it
Right,
doesn't really matter what the network did to it's that's not the explainability problem that you're trying to solve. You're just
right.
trying to explain the end result.
Yeah, yeah. it's
or
yeah
the
they
intermediate result, not really the end result.
yeah
Yeah.
right yeah.
Okay. And you mentioned some other challenges that you're looking forward to solving.
Yeah, so in terms of how to just so there's some problems that in the field that people identify, like the cross domain generalization. So this spider benchmark looks at cross domain generalization already, but it turns out when you're if you try to generalize to a different data set that are collected different under a different policy, like for data collection,
Hmm.
the accuracy drop is pretty big, as we all expect from machine learning systems.
Yeah.
Like so how to um, make the model more robust, not just across domain, across the database that are sort of more or less collect under the same data collection protocol, but to things that are very different in the wild. That's still a big open problem.
Hmm.
Yeah.
Possibly relating back to the data augmentation problem as well, right?
Yeah, yeah, that's definitely a big part of it. Yeah,
Awesome. Awesome.
yeah.
Well,
Thank,
Yanshuai, thanks so much for taking the time to share a bit about what you've been working on. It's very cool stuff.
thank you very much, Sam. Thank you for having me.
Thank you.